All right, welcome to our 15th video of Unit 7. This is ionization energy. So, here we go. The ionization energy of an atom or ion is the minimum energy required to remove the least tightly held electron from the ground state of the isolated gaseous atom or ion. Basically, it's the lowest energy possible to pop off an electron. That's really what it comes down to. In general, the first ionization energy is the energy required to remove the first electron from a neutral atom. The second ionization energy is the energy needed to remove the second electron, and the third is the third, and the fourth is the fourth, etc. You see the pattern. As we take more and more electrons from atoms or ions, we are taking them from increasingly positive ions. Now, every electron, therefore, taken from an atom will have a different ionization energy. Now, let's think about this. If I have something that we take, we got a 1+ charge on, that says that we have one more proton than our electrons, which means that compared to when we were neutral, there is now a tighter pull on the electrons. So, just by the fact of protons and electrons, the more electrons we take away, the harder it's going to get. Secondly, sometimes when you take away electrons, let's think of sodium plus. If I have sodium with 1+ and I take away an electron, sodium now basically looks like neon in that it's 1s2, 2s2, 2p6. If you try and take one more from that, sodium's going to trip out. Like, it's going to say, what are you doing? No. It's very stable. The repulsions and attractions are very balanced. It's going to be very hard to disrupt that balance. So it's going to take a lot of energy. So sometimes, just for the fact that you're taking more electrons is harder. Sometimes they're in a state that's stable and it's really hard to disrupt that. So anytime you're looking at a chart of ionization energies and you see the spike somewhere, likely it's coming from, like, at that point is in a very stable condition and you're trying to disrupt that. So keep that in mind. So let's do a brief kind of introduction just to make sure you know the terminology. I'll give you a bit. Go ahead and try this. Come back in like a minute or two. Have fun. All right. Welcome back. So for sodium, the first ionization energy is you start with a stable thing of sodium, and you end up with sodium plus and an electron. The second is you're starting with sodium plus, which again, this one typically doesn't normally happen, but you're popping off another electron, so you've now got 2+ and 1 extra electron. Those are ionization energies, okay? Often, like I say, they'll be given a chart with numbers, but it really just comes down to knowing kind of what's happening. So, in general, smaller atoms have higher ionization energies. Basically, the electrons are closer to the nucleus. They can hold on to them stronger. So, keep that in mind. The energy needed to remove an electron from the outermost occupied shell depends on both the effective nuclear charge and the average distance of the electron from the nucleus. Something about charge and distance. That reminds you of something. Interesting. Maybe it's because the higher the charge, the more force we're going to be required, and the closer it is actually to the nucleus, the stronger this force is going to be, which may explain why it gets harder as we remove more and more electrons because our charges get higher, and small atoms actually require more force or more energy to take away their electrons. It's like Coulomb's law was built for that reason. So either increasing the effective nuclear charge or decreasing the distance from the nucleus increases the attraction between the electrons and the nucleus according to Coulomb's law. I'm going to pretend that I knew that was here. Totally didn't. But there you go. Coulomb's law. Again. I really got to start actually reading ahead before I do these. Oh well. In addition, valence electrons of larger atoms are easier to remove than those of small atoms due to electrons being shielded from the core. Because the farther out you get, the more electrons there are between the atoms, and thus they're basically shielded. They've got less attraction. You can pull them off easier. So that means our ionization energy will be less for those. As that attraction increases, it does become more difficult to remove the electron, and so our ionization energy will increase because it takes more energy to remove an electron. So, referring to the periodic table, basically our trend, hopefully you caught on, is that the smaller the size, the bigger it is. Well, atomic size, basically our biggest was down here and our smallest is down here. Up there. So this says that our trend then, which basically means that our trend for ionization energy is the exact opposite. Because the bigger it is, the smaller our ionization energy, and the smaller the atom is, the bigger our ionization energy. That means it will decrease going down and increase going across. So with that, go ahead and sort these atoms. Come back in a bit. All right, so welcome back. Here's basically a rough sketch of where these atoms are in the periodic table. So if we're doing increasing, our smallest is down here, and our biggest is up here. By the way, that means that it's very easy for these to lose electrons, very hard for these to lose electrons, meaning these are normally going to form positive charges. These normally won't. Hey, that makes sense. Metals form positives, non-metals don't. Anyways, our smallest and going up will be K, Na, P, Ar, Ne. That's our order. Again, going big, getting that way. Getting big, going that way. Wow. All right. Thanks for watching. That's ionization energy.